Hello everyone. What we'd like to do in this video is let's just do some more examples of computing compositions and finding its domain. Okay, so for our first example, let's say we have the function, let's say f of x is equal to, let's say it's 3 all over x squared minus 1, and let's say g of x is equal to, how about the square root of x plus 3. What I would like you to do is I want you to compute f of g of x, and I want you to find its domain. Go ahead and pause the video and give that a shot on your own. Okay, let's do it together. Let's first compute the composition. So what we're doing here is we're taking g of x and we're plugging that in to f of x. Okay. So what does g do to a function? When I plug something into, plug an x value into g, it adds 3 and square roots it. So I'll take that number x, we'll add 3 to it, and we'll square root it, and we're going to take that result and feed it into f. So now wherever I see a x in f of x, I'm going to replace that with the square root of x plus 3. So we're going to get a 3 all over. We'll have the square root of x plus 3 squared minus 1. Let's clean this up a little bit. The square and the square root cancel each other out. I get a 3 all over. I'm going to get an x plus 3 minus 1. I'm always a little bit careful about parentheses here. For example, in these examples, I don't need parentheses, but let's just pretend for a second it was like a 1 minus the square root of x plus 3 quantity square. The square and the square root would cancel each other out, but I would need to have parentheses on the x plus 3 and remember to distribute that minus sign. So in general, I'm very paranoid with parentheses. I'm always introducing them, making sure, can I remove them? Do I need to distribute something into them? So I'm always very careful with parentheses. In this case, there's nothing to distribute, so these parentheses aren't doing anything for us. Okay, so we're going to get a 3 all over. Well, I'm going to get x plus 3 minus 1. 3 minus 1 is 2, so I get an x plus 2. So what we have here, let's actually write this up here. We have that f of g of x is 3 all over x plus 2. So now what we need to do here is we need to find its domain. Now remember, there are 2 places we need to check. So if I'm drawing this picture again, what did we do? We had our function g and we have our function f. Okay, we're plugging something into g. It's spitting something out and it's being fed into f, and that's spitting something out. Okay, so what we need to check here is I need to check first, what is the domain of the inner function? I have to check what am I allowed to plug in? So looking at g, what we need here is we need x plus 3 to be greater than or equal to 0, because I can't be taking the square roots of negatives. So we have x has to be greater than or equal to negative 3. So I'm going to write over here, when we check the domain of the inner function, we have that x has to be greater than or equal to negative 3. So I can plug in values only that are bigger than negative 3. Now, the problem is this set right here, this is the biggest possible set that could possibly be the domain, but I might have to shrink this because for some of these x values, the outputs may not be accepted into f. And that's why we also need to check the domain of the outer result. So when I'm checking the domain of the final result, what that's doing is it's making sure that the outputs of g were able to go into f. So I need to check also the domain of the end result, the ER, I guess. So when we look at our end result here, what we see here is, notice that x cannot be equal to negative 2. Otherwise, we'd be dividing by 0. So notice here that x cannot be equal to negative 2. If we tried to plug in negative 2 into this function, we'd have a problem. Let me just illustrate this for you. What if we tried to plug negative 2 into g? So we're going to get what? G of negative 2. Well, That's going to give us negative 2 plus 3. So we're going to get the square root of 1, which is 1. So when you plug in negative 2, it's going to spit out 1. But if I try to feed 1 into f, f of 1, that's 3 over 1 squared minus 1. That's 3 over 0. We can't divide by 0. So when you're checking the domain, of the end result, you're making sure that the outputs of G can be plugged into F. That's why we have to check 2 locations. So now we have the domain. It's going to be the intersection of these 2. So let's sketch that. I'm going to go ahead and erase what I have here. Okay, well, this is saying that x has to be greater than or equal to negative 3. So here's negative 3. X has to be greater than or equal to negative 3. Okay, let's do this one in green. This is saying that x can't be equal to negative 2. So here is negative 2. So for x not being equal to negative 2, that's all values except negative 2. I need to find the intersection of these. And that's just going to end up being the region. Here's negative 3. Here's negative 2. This will be our domain. We could write this in a couple different ways. Maybe I'll erase some of the pieces over here. Okay. So I could write it in set builder notation, which is my personal favorite. So this would be all x such that x has to be greater than or equal to negative 3, and also x cannot be equal to negative 2. It's probably not going to be very often that WAMAP is going to want you to use this type of notation, so that's why I'm making sure to try to show you other notations that WAMAP might ask you to use. So let's say if we wanted to use, let's say, what is it called? I always got interval and inequality. Interval notation, that's where you use the brackets. So I have these 2 regions. So this one right here, I'll kind of glue them together. So I have this set, which would be from negative 3 to negative 2, hard bracket, soft bracket, or we could be from negative 2 to infinity. So that's another way to write the domain. Okay. Let's try another example. Let's actually do the reverse composition. This one's a little bit more challenging, but let's give it a shot. Let's try and compute g of f of x. So I want you to compute this composition, and I want you to try and find its domain. Go ahead and pause the video and give it a shot. All right, let's do it. So what are we doing? We're taking f of x, the outputs of f, and we're plugging those into g. So what does f do to a number? Well, it looks like it squares the number, it subtracts 1 from it, and then it takes 3 and divides it by that result. So once that computation runs through, this would be the output of f. And then this output is going to be fed into g, so wherever I see an x in g of x, I'm going to replace that with a 3 over x squared minus 1. So here, let's actually write it right here. We're going to need a little bit of room here in a second. So we have a 3 all over x squared minus 1. I'll put parentheses here. That's replacing the x there. It's always a good idea to introduce parentheses when you're inputting something in for x. Just because, I'm paranoid all the time about messing up distributing a negative or some sort of, something I might miss if there weren't parentheses there. But notice here there's nothing to distribute, so these parentheses are not needed. Okay, this is fine for a composition. This really is the composition, but I would like to clean this up a little bit. It's going to be a lot nicer to work with, specifically when I'm trying to find the domain of this, if I actually go ahead and do this fraction addition. Think of this as 3 over 1. We're going to go ahead and find a common denominator and clean this up a little bit. So let's do that over here. We have 3 over x squared minus 1 plus 3 over 1. Let's use the best trick in the math book, cleverly multiply by 1. Let's multiply by x squared minus 1 all over x squared minus 1. Notice I'm using parentheses because I'm paranoid. Okay, they'll have a common denominator, so we can add their numerators. So we'll get a 3 plus a 3 times an x squared minus 1 all over our common denominator of x squared minus 1. Notice that I'm paranoid about parentheses. Well, look, I have to remember that I need to distribute this 3 in. So we're going to be left with, looks like a 3 plus a 3x squared minus 3 all over an x squared minus 1. No way. The 3 and the negative 3 cancel each other out. So moving it up over here, looks like we get a 3x squared. We get a 3x squared, sorry I'm blocking the board, x squared minus 1. Okay. So I'm just going to go ahead and replace this up here. So we have 3x squared all over x squared minus 1. Okay. So recall we need to check two places. What were we doing? We're plugging something into F, and the output's being plugged into G. I need to make sure that F, I can plug things into F. I need to make sure the outputs of F can go into G. So let's first check the domain of the inner function. Okay, our inner function here will be F. I need to look at the domain of F. Let's take a look here. If I'm looking at the domain of F, well, I'm not worried about taking the square root of a negative, but I am worried about possibly dividing by 0. Notice that this is the same thing as 3. I can factor the bottom. This is x minus 1 and x plus 1. So the domain of the inner function, notice that x can't be 1 and x can't be negative 1. X cannot be 1. And x cannot be negative 1. Okay. I also need to make sure that the outputs of f can go into G, so to check that, I'm going to check the domain of the end result. So let's look at the end result. Okay. So looking at this piece right here, since there's a square root here, I need to make sure that what's inside of the square root is positive. So what we need here is we need 3x squared, and for right now I'm going to go ahead and factor the denominator. X minus 1 times x plus 1. We need this to be greater than or equal to 0. Notice that this is a rational function, and we're asking ourselves the question, when is this rational function above the x-axis? When is it bigger than 0? So to think about when this is true, we need to think about when can a rational function possibly flip signs. It can only possibly flip signs if it's going through the x-axis, it has to go through an x-intercept, or it could possibly flip sign on an asymptote. So I need to find the x-intercepts, and I need to find the vertical asymptotes, and I need to do a sign chart. So let's go ahead and do that. Okay. So the x-intercepts, remember, for a rational function come when the numerator is 0. The numerator is 0 when x is 0. I also have, let's see here, we have I'm going to put a z here. This is when we plug in, this is the value that makes this 0. Okay, notice that this function is undefined at x equals 1. I'll put a u here to note myself that my function is undefined here. And also at negative 1, the function is also undefined here. These are where the vertical asymptotes would be. So I know that the only way this function could flip sign is, by going across negative 1, going across 0, or going across 1. So we can make a sign chart here. We could also piece together, we could piece it together even without checking values if we wanted to think about it. Well, one thing you could do is you could notice what's the end behavior of this function as x gets really, really large. Notice here I have a second degree polynomial over a second degree polynomial. The numerator and denominator are tied in the war. They'll settle on the ratio of their coefficients, which is 3. So this function here, its end behavior will be 3. It's positive, so I know way over here it must be positive. Similarly, it'll do the same thing for the on the negative side. It'll also approach 3. If you don't like that argument, just test a point. So just pick something bigger than 1. How about 100, for example? Well, if I plug in 100 here, I'm going to get 3 times 100 squared. Well, that's going to be something positive. Okay, 100 minus 1 is still something that's positive. 100 plus 1 is still something positive. A positive number divided by a positive number will be positive. Similarly, you could check something over here. This could be negative 100, something way over here. In a similar way, if I plug in something super, super negative, if I square a negative number, it becomes positive. I'm multiplying it by a positive number, so it's still positive. Negative 100 minus 1, well, that's a negative number. And negative 100 plus 1, that's still a negative number. So I have a positive over a negative times a negative. I get a positive over a positive. That's positive. Okay. We could use our tricks of how rational functions behave to figure out the behavior here without checking any points. Notice here I could think about the multiplicity of the asymptote, vertical asymptote x equals negative 1. Well, it has a multiplicity of 1, so it has opposite action. So if it's approaching this way, it's going to be approaching down on the other side. So it should be negative here. Again, if you don't like that argument, what we can do here is we could test a point. What's the number between 0 and negative 1? How about negative 0.5? If I take negative 0.5 and I square it, that'll be positive. If I take negative 0.5 and I subtract 1, that's still negative. And if I take negative 0.5 and I add 1, that's positive. So I have a positive, a negative times a positive is a negative, a positive over a negative is negative. Okay, now I have a 0 here, so the question is it going to cross through this x-intercept or is it going to bounce? Well, if I look at the multiplicity of that 0, the multiplicity is 2, it should bounce. So if you don't like that, I mean, it should bounce, so it should, in this case here it was negative, so it should bounce and stay negative. So I'm going to argue that it should still be negative here. However, what we should do is we should check this. I mean, if you don't like this argument, pick a number between 0 and 1. How about 0.5? If I take 0.5 and I square it, that's going to be positive. If I take 0.5 and I subtract 1, well, that's still going to be negative. And if I take 0.5 and I add 1, that's still going to be positive, so I'm still going to get negative. And again, the reason is it bounce is I'm looking at the behavior around 0 since this number is being squared. You know, if I'm over here, x is negative. If I'm over here, x is positive. But since I'm squaring it, it's going to be positive. This piece won't flip sign when I move here, and that's why it has the same behavior. The reason it's negative is this piece right here. If I'm at negative 0.5, this piece is negative, and if I'm at 0.5, this piece is still negative. This piece won't flip sign until I'm starting to look around the behavior of 1. So this multiplicity is telling me it's going to bounce. Okay, so I need to figure out when is this function bigger than 0? Well, looking here, that's when, well, what? That's when x is strictly less than negative 1, and also when x is strictly bigger than 1. So the domain of our end result is that x has to be less than negative 1, and also x has to be greater than 1. So I need to find the intersection of these two sets. So if I'm looking for the intersection, okay, well here this is saying that x can't be 1, so here is 1, x can't be 1, and x can't be negative 1. So this is saying all numbers except 1 and except negative 1. This right here is saying that x has to be strictly less than 1, and also x has to be bigger than 1. So I need to find the intersection of these. That's going to be these two regions here. So what we'll have here is the domain of g of f. That's going to be all x such that, well, x could be less than negative 1, and also x could be bigger than 1. Or if we want to write this in interval notation, we could be going from negative infinity to negative 1, or we could be from 1 to infinity. So both of these would be 100% correct. A little bit challenging, but really using our skills from 3.6 really helped out with this problem. Let's do another one. All right, here's our next example. What I want you to do is I want you to try to compute f of g of x and find its domain. Go ahead and pause the video and give that a shot on your own. All right, let's do it. So what are we doing? We're taking the outputs of G and we're feeding them into F. So what is G? G is x over x plus 2. So wherever I see an x in f of x, I'm going to replace the x with an x over x plus 2. So 2 all over, in parentheses, x over x plus 2. And what do we have here? We got a complex fraction. Those of you who just took 99, maybe you thought these would never come back, but here they are. How do we clean this up? Okay, what I'm going to do is how I'm going to read this. A complex fraction is like a fraction within a fraction. Notice I have two fractions within a larger fraction. So what is this saying? This is saying I'm taking 2 over 1 and I'm dividing it by an x over x plus 2. So remember how we divide fractions, we flip and multiply. So this is 2 over 1 times an x plus 2 all over x. I'm going to be paranoid about parentheses here. Okay. So now we're going to multiply straight across, and let's see what we're going to get here. We're going to get a 2 times an x plus 2 all over a x. Okay. So if you would like, you could distribute in that 2. You could distribute in that 2. And you could write this as a 2x plus 2x plus 4 all over x. I would accept either one. Neither one is more simplified than the other. I'm just going to keep it factored. Okay. So now let's go ahead and find its domain. Okay. So let's see what we're doing. We're first plugging something into G, and then we're plugging it into F. So I need to make sure what I plug into G is accepted. So I need to look at my inner function, our inner function. Okay, our inner function. Let me see if I can fix that glare real quick. Open the window because it's really hot in here. Okay, hopefully that's a little bit better. Okay, so for our inner function, see, what can't we do? What can't we do? We can't plug in -2. I'd be dividing by 0. X cannot be -2. Okay, now I need to make sure that the outputs of F can go into, the outputs of G can go into F, so I need to check our end result. Our end result, okay, well looking at our end result, I can't plug in 0. I can't plug in 0. And look why, look why. What happens? What happens when I plug 0 into G? When I plug 0 into G, I'm going to get a 0 over 0 plus 2. I get a 0 over 2, which is 0. Can I plug 0 into F? Heck no! Heck no, I'd be dividing by 0. I can't plug in x equals 0. So our domain. Okay. If you would like, you could just write that x can't be -2 and x can't be 0. I think it's nice to see a number line. You don't have to always do this. I always try to show a lot of gory detail when I can. So if we were to sketch this, what x can't be -2 and x can't be 0. So x can't be -2, x can't be 0. Okay. So if we want to write this in set builder notation, we would just say all x such that x can't be -2 and x can't be 0. Or if we wanted to write this in interval notation, we could say, let's see, we could go from negative infinity to -2, or we could go from -2 to 0, or we could go from 0 to infinity. So either of these would be 100% credit. I think WAMAP most likely is not going to want you to, type in set builder notation. Set builder notation is very common, and I want to make sure that we understand how to read it and how to use it. But WAMAP will most likely have you input it in interval notation. Okay, let's try another example. You can probably guess what we're going to do next. We're going to do the opposite composition. Okay, so what I want us to do here is I want us to compute what we just did, fog. Let's do GOF. Let's compute G of f of x. Go ahead, pause the video, find this composition, find its domain, and we'll do it together. All right, let's do it. Okay, what are we doing? We're taking the outputs of f and we're plugging those into g. Okay, so I'm doing g of, what's f? F is 2 over x. So wherever I see an x and g of x, I need to replace that with a 2 over x. Notice this is probably our first example that we've seen where there are two locations where I need to put the 2 over x. So I'm going to be paranoid with parentheses all over a 2 over x plus 2. They weren't necessarily needed, but I'm just paranoid all the time. I don't know specifically with parentheses. Okay, so how are we going to clean up this complex fraction? All right, there's two ways you could do this one. I'm going to use a different method than I used last time, and I'll actually show you two different ways to do this. So the way I'm going to clean this one up is I'm going to use the best trick in the math book. I'm going to cleverly multiply by 1. Okay, I want to multiply by a 1 that'll clear the fractions in both these pieces. I need to be able to clear an x, so I'm going to multiply top and bottom by x. I'm cleverly multiplying by 1. And what we're going to do is we're going to distribute that into the parentheses. Okay, so this x will hit the 2 over x, and this x will hit the 2 over x and the 2. So what will we get? This will be a 2 over x times the x. You could think of that as an x over 1 if you like. All over a 2 over x times an x over 1 plus a 2 times x. So this x is hitting all these pieces. Notice, these x's cancel, heck yes. And these x's cancel, heck yes. What are we left with? Okay, in the numerator, we're just going to be left with a 2 over 1, or we're just going to be left with a 2. And in the denominator, we're just going to be left with a 2 over 1, or how about a 2 plus 2x. There we go. Okay, we could go ahead and clean this up. Don't go cancel crazy. You can't cancel these 2's. You can't cancel this 2 and this 2 because these are common terms. I need to find common factors to cancel. So I need to factor a 2 out of the bottom. 1 plus x. Okay, notice that, think of there's like a 2 times 1 here. These 2's will cancel. And we're just left with a 1 over 1 plus x. Okay, so maybe I'll leave this here for right now. I'm going to show you a different way to clean up this complex fraction. If you're already comfortable with it, feel free to fast forward the video. You can do that with a lot of my videos. If you are comfortable with the spot, you can kind of fast forward if you'd like. So, let's see. What's another way to clean this up? We have a 2 over x. The other way I'm going to do this is I'm going to try to find a common denominator in the bottom, so this is a solid fraction, so then I can flip and multiply. So I could write the bottom, how about as a 2 over x plus, let's cleverly multiply by 1 here. Let's multiply 2 by x over x. So then here we have 2 over x plus 2x over x. Now that I have a common denominator, I can add across the numerators. So this is a 2 over x all over a 2 plus a 2x all over x. I'm taking this fraction, I'm dividing by this fraction. We can flip and multiply. So we'll get a 2 over x times a x all over a 2 plus 2x. Okay, maybe still being a little bit paranoid about parentheses. Okay, notice when these multiply together, I got another one of those secret 1's lurking in the bushes. The x over x, heck, that's just 1. Okay, now when I multiply these together, I think there's still times 1 right here. I'm going to get a 2 times 1, I'm going to get a 2 all over. There's still kind of a hidden 1 here. 1 times 2 plus 2x, I get a 2 plus 2x. It's the same, it's the same, it's the same. Great. So either of these methods are great for simplifying complex fractions. In this situation, I thought it was much easier to think about clearing the fractions. If you're uncomfortable with that method, just stick with what you know. Find a combinator, flip, multiply, simplify. Okay, so either way, we're still going to be left with a 1 over 1 plus x once you factor out this 2 and cancel. Okay, let's find the domain. Let's find the domain. So, the composition. A 1 over 1 plus x. Okay, let's find the domain. What are we doing? We're plugging something into F, and those outputs are going into G. Okay, let's check that we know what I can plug into F. I need to check the inner function. Okay, what What can't I plug into the inner function? Ah, I can plug in anything but 0. X can't be 0. Okay, what about the end result? I want to make sure that the outputs of f are okay to be plugged into g. So looking at our end result, well, notice that x can't be equal to -1, or I'd be dividing by 0. Okay, let's go ahead and write this. Let's write the domain. So if we want to use set builder notation, my favorite, be all x, such that what? X can't be -1 and x can't be 0. Okay, if we want to write this on a number line, if we want to use the other notation, here's -1, here's 0. Okay, let's see, what can we do? We can go from -infinity to -1, or we can go from -1 to 0, or we can go from 0 to infinity. Both of these, 100% credit. I don't know, I just find this fun to do. Why can't x be equal to -1? Well, what happens when I plug -1 into f? f of -1 is 2 over -1. That's -2. Well, can I plug -2 into g? Nope! Nope! If I plug in -2, I'd be dividing by 0. So when I was checking the domain of the end result, I was making sure that the outputs of f could be plugged into g. And there we have it. Here's the composition. Here is the domain. I wrote it in 2 different ways for you. I hope you're having fun with these compositions. I know I am. We'll see you in the next video. Take care.